Hello students, in this video we'll discuss distance in the extended complex plane. Let's recall the stereographic projection phi takes a point in its sphere and maps it into the complex plane adjoined infinity. Right? Where, of course, how does this constructed? It's constructed in a way where phi takes the North Pole, phi the North Pole is infinity, right? And then every other point on the sphere is the intersection between the North Pole and the complex plane. It's how are the other points defined? The other points are defined as follows. We have the unit sphere, right? The hemisphere, the equator, is in the complex plane. Okay? And then here's the North Pole. For any point z in the complex plane, we just simply drop a line segment from the North Pole to z, and that's going to intersect at a unique point p. And so in other words, the stereographic projection defined by phi of p is equal to z. We already found the formula for this in the last video, right? We found the formula that phi, that if z is equal to x plus iy, that d it's going to be z plus z bar over mod z squared minus 1. And then what? And then also it's going to be what? Then z bar minus d times I over mod z squared minus 1. And then finally mod z squared, that's a plus 1 actually, plus 1. Mod z squared minus 1 over mod z squared plus 1. That's our corresponding z, then d. And of course, this is really what? This is really nothing more than just x squared plus y squared, right? Modulus of z. And so what we can do now is we can write down the points of, let's first put this into spherical coordinate, right? So the point x1, x2, x3 on the sphere, on S2, also has the spherical form, it's going to be a cosine of phi sine of theta, and then sine of phi sine of theta, and then find out what the cosine theta, like that. Beautiful. Okay, now of course this is really what we want to do now. We want to try to figure out a formula for what this stereographic projection is in terms of the complex point over here, right? So how can we do that? So what do we know? So we're going to have what? So we can conclude from this actually that this z first is going to be what? The z component is going to be what? Is going to be x1 plus I x2 over 1 minus x3, like that. Okay, so that's our formula for the z in terms of the x, y, and z from the stereographic projection, right? Excellent. And we can easily check what the 1 minus x3 is, right? Because that's going to be like my t over here. Excellent. Okay, good. So that's our formula for z. Now let's put this in and see what we get over here. So of course, we really want to check that this gives us exactly what we want, right? And so if I have x1 over here, the x1 component over here is going to be z plus z bar, right? And then 1 minus x3 is just going to give me a factor of 2, right? So that's going to cancel out the real part. So that gives me the real part. Then similarly over here, so in other words, we know that the x3 is this, and 1 minus x3 is going to be 2 over mod z1 plus z2. And so that gives me exactly the real part. That gives me the imaginary part. So everything balanced out correctly, right? So that's the formula for z in terms of x1, x2, and x3. So let's fill in what the x1 and x2 is, right? So what's x1 going to be? x1 is going to be cosine of phi sine of theta, and then plus I, and then what? Then a sine of phi sine of theta over 1 minus the cosine of theta, right? That's my x3 is. Now, look at these terms over here. These terms both have a factor of sine of theta, all right? So this is going to be sine of theta times what? Times cosine of phi plus I sine of phi, all divided by 1 minus cosine of theta. Now, of course, that's in the theta. So what's my formula for z in terms of the phi and theta? So this mapping z, then we're going backwards. If I go from the z to a point on the sphere, if I go from the point x, y, z, if I think of z as the point x, y, z, and the sphere as the point z, then what can we say? The formula of stereographic projection in these coordinates over here is going to be what? So it's going to be equal to sine of theta over 1 minus cosine theta times e to the I phi. Excellent. And so now, so in other words, this point over here, this is a point in the complex plane, right? This is a point in the complex plane that corresponds to what? That corresponds to the point in the sphere that has longitude and latitude phi and psi, right? So we'll formalize this. Now, what's the important lemma? We'll simplify this a little bit. So this comes up all the time in trigonometry. If you think back for days, right? So that's like the half angle formula for tangent, I think, right? So here's a side. The tangent of what? Of theta over 2 is the sine of theta over 2 over the cosine of theta over 2, which is the square root. Sine of theta over 2 is 1 minus the cosine of theta over 1 plus the cosine of theta. And so if I rationalize this by a 1 minus the cosine of theta, 1 minus the cosine of theta, then this becomes a 1 minus cosine theta over, this would be sine, so that's going to be a sine of theta. So that is not the tangent of theta over 2, that's the cotangent of theta over 2, right? And so we have our formula for this stereographic projection in spherical coordinates, right? If I look at this function over here, phi, which takes a theta and a phi to what? Takes a theta and a phi, takes the point in the sphere and maps it to what complex point? Maps to the complex point cotangent of what? Of theta over 2. That gives us this thing, e to the I phi. That gives us our spherical representation of this stereographic projection over here, right? And of course, we can think about what's going to happen in the instance when with theta over here, your theta is going to be your they're going to be the meridian angles, right? And so when theta is equal to 0, right, that means that 0, 0, 1, you're at the North Pole. So when theta is equal to 0, that's where the cotangent has a singularity, right? That's where you're going to infinity, right? So remember, the cotangent looks like this. So here's the cotangent function. Cotangent has this sort of a structure over here. There's pi over 2, like that. That's the graph of cotangent. There's our theta axis, and there's the f of theta axis. There's the cotangent of theta over 2 axis. And clearly when theta goes to 0, as theta goes to 0, the cotangent of theta over 2 goes to infinity, and that matches what we know about the North Pole being mapped to infinity into the stereographic projection, okay? Now, we're in a great position because now I can use these definitions to define distance in the extended complex plane. So let's let Z1, Z2 be in C. And I'm going to find the distance between these 2 points. I'm going to find the distance just to be the distance between the corresponding points in the on the sphere, right? These corresponding points on the sphere. So this is like the extended distance, right? So this is going to be what? This is going to be some different notation over here. So what we're going to do is we're going to call Z1 is going to come from, so let's say that Z1 is mapped to by phi by the point, let's say x1, x2, x3, and Z2 is mapped by x1 prime, x2 prime, x3 prime. Okay, let's do it like that. And so this is going to be the distance, ordinary distance over here. So this is going to be x1 minus x1 prime squared plus x2 minus x2 prime squared plus x3 minus x3 prime squared, like so, to the power 1/2, of course, right? So in other words, the distance between 2 points in the extended complex plane is just the distance between them on the sphere, right? Because they're on the sphere. Now, since they are on the sphere, what can we say? The x1 squared, x1 prime squared, all those are going to add to 1. So this is really just what? So the distance squared, I'm going to say distance extended squared of Z1 and then Z2 is really going to be 2 minus 2 times what? x1, x1 prime, x1, x1 prime plus x2, x2 prime plus x3, x3 prime, like that. Easy enough. Now, of course, what we can do is we can simplify this dramatically over here, because what can we say? I have an x1 times x1 prime. That's going to be the z1 bar. And then the i's have these things and these things over here. So if we do this calculation, we're going to see this is going to simplify to what? If we simplify this, we can conclude that the distance extended in z1 and z2 just by pulling this out. So just a little bit of algebra, right? So z1 bar prime, z1 bar, yeah, so I'll have the, in this terms over here, I'll have the z1 plus z1 bar times z2 plus z2 bar, the same thing over here, and then these things over here are going to stay the same. So we can conclude from this, if I do this calculation, this is going to give me 2, the distance between z1 and z2, the ordinary distance, over 1 plus z1 squared, the 1/2, times 1 plus z2 squared. Like, so distance, this formula, so just simple calculation. And then what? Of course, you can see that you can get a what? When you square this out, when you square all these things, you're definitely gonna see this factor and this factor in the denominator, right? Because that comes with z1, that comes with z2, and the rest is just to figure out that u and this b squared. Now, the last thing over here, the simpler case is that if I look at the distance extended in the extended complex plane between a fixed point z and the point infinity, what's that going to correspond to? It's going to correspond to the point. It's going to correspond to the point 0, 0, then 1 for x3 prime. So all the x2 are going to be 0 except for this last one over here. So we're just going to get 2. So in other words, what's going to happen is this is all going to simplify over here. It's all going to simplify to what? It's all going to simplify just to 2 over 1 plus mod z squared to the power 1/2. And so in other words, I'm able to use these formulas over here by plugging in the corresponding values. This is going to give me a what? That's going to be a 0. That's going to be a 0. That's just going to be an x3, right? And that's going to give us this thing over here. Well, of course, the z's aren't going to cancel out. You're just going to get 2 in the numerator over what the mod z is, right? So that's just simple algebra calculation. So this defines a distance. Distance extended is a metric on the extended complex plane, C united with infinity. And eventually we'll start to talk about some of the topology of this space over here, but this is also referred to, this space over here is what's known as the one-point compactification of the non-compact space C. If you have a non-compact space, one of the most elementary things to do is to take the non-compact space, put some points infinity on there, and put a version of the stereographic projection, because this mapping over here is clearly a bijection between the sphere and the extended complex plane. I have a bijection, so that allows me to define continuity, limits, differentiability from the complex plane onto this via this stereographic projection, and I now have the metric structure on the extended complex plane for me to perform any analysis I wish. Thank you very much.